Good afternoon and welcome to MAE 209 Probability and Statistics. My name is Richard Kohar and this is Lecture 19, the Gamma Distribution, and that covers section 4.4 in our textbook, and we'll also be talking about discrete jointly distributed random variables, and that covers 5.1 and 5.2 in the discrete case. Hopefully everyone can hear me okay. Okay, perfect. Yes, there was a little bit of a hiccup when it came to Moodle, so I sent out an email. Unfortunately, the PDF of my skeleton notes or the fill-in-the-blank version wasn't available, so hopefully everyone got the email and is able to join. So a couple of announcements. Midterm 2 is this Thursday, the 24th of March, 2022. It's in person. It's going to be in closed book. And it's in Girard, let me just double check that. Yeah, just a second. Okay, so that will be that's posted on Moodle. If not, I'll have to send out another email. The formula sheet is provided, it's posted on Moodle, and a standard normal table will be provided as well. There's a non-programmable, non-graphing scientific calculator you're allowed to bring. Yes, G133, thank you. So I'll put that down. We'll have 6 questions just like the last midterm. One of the questions you'll have to prove or show something. And again, one of these proofs we had done in lecture, so you should be fine if you were following along. It will be covering sections 3.4, 3.5, 3.6, 4.1, 4.2, 4.3, 4.4, and 5.1 and 5.2 for the discrete case. We're going to start at 8:05 a.m. and there's 60 minutes for it. Okay? So, we have to cover some material today. The first thing is we're going to talk about the gamma distribution, but before we get to that, we have to talk about the gamma function itself. So it's a function that keeps popping up in calculus, and here's the gamma. It's the gamma of alpha, and alpha is the parameter, which is greater than 0. Yes, it is a proof that you have seen before. And yes, there will be a lecture on after the midterm on Thursday. And so this is the integral from 0 to infinity of x to the parameter alpha minus 1 e to the minus x dx. There's 3 properties for that. And you can write it as a recursive definition. So you can write gamma alpha is equal to alpha minus 1 times gamma alpha minus 1. So that's kind of like a recursive definition. The second one is that if n is a natural number, and again, natural meaning it's a counting number, 1, 2, 3, 4, that if you take the gamma of a natural number, it equals n minus 1 factorial. And so if you forgot what factorial was, that is where, for instance, I have 5 factorial is equal to 5 times 4 times 3 times 2 times 1. So if you have a number like gamma 3, then it's equal to 3 minus 1, which is 2 factorial, and 2 times 1 is equal to 2. The next thing is that if you take the gamma of 1/2, the fraction 1/2 is equal to the square root of pi. Now, the gamma distribution has this PDF. It's 1 over beta to the alpha times gamma alpha times x to the alpha minus 1 times the exponential function to the x over beta. And that's for a value of x which is greater than or equal to 0. And if it's negative, then it's 0. So we have those two parameters, the alpha and the beta. And depending on what parameters you have, it can look like something like this, or it can look like something like that, or it can go like that. So it depends on what those parameters would look like. So to give you an idea of what the PDF would look. If beta is equal to 1, then this is called the standard gamma distribution. And so all I've done here is I've replaced the beta with 1, so that goes to 1. So I'm just left with the gamma of alpha. And then I'm left with the x to the alpha minus 1. And the exponential, or the exponent, simplifies from minus x over beta to just e to the minus x. What's interesting that if you set the alpha equal to 1 and the beta equal to 1 lambda, then you get the exponential function. So looking at this, you can actually get something to look like that. So why it's kind of useful for us is that the gamma distribution can model a lot of different curves. And it's the flexibility that allows us to model a lot of situations. So with that, we had the PDF, which was this function. Now, if we take the integral of that, that will give us the CDF. So doing that, this is what we get. Now what's interesting is that I'm not going from 0 to beta, but instead I'm going from 0 to x over beta. And the reason for that is because we can use this, we can actually use a standard gamma distribution. And like I said, the standard is when beta is equal to 1. So just like how we had with the normal distribution, we had the standard normal distribution. We also have, with the gamma, we have a standard gamma. And that means that we have a table that we can look up the values for the CDF. So what does that mean? There's a way to calculate it using a table. And so what I do is I can have this, and I can rewrite it in terms of just one parameter, because the standard gamma is written with just one parameter, which is the alpha. So if we replace that alpha with the alpha over beta, then we can use what's called the incomplete gamma function table, which is given by this. And let me just grab that formula. Over here, this is what we call the incomplete gamma distribution. So there is our standard gamma distribution, where the beta is 1. And so there's our formula. And you can look up the alphas for 1, 2, 3, all the way up to 10, and from x from 1 to 5. So it's a very small table, but it's, for our purposes, it will help us to demonstrate some of the calculations that we'll do. Along with the gamma distribution, we've covered the PDF, the CDF, and now for the expected value, it's just alpha times beta. So we just multiply the two parameters together. And for the variance, we multiply alpha times beta squared. So this is our first example. Suppose that the reaction time of a randomly selected RMC officer cadet to a certain stimulus follows a standard gamma distribution with alpha equals 2. So then in part A, what we're asked is, what is the probability that the reaction time will be between 3 and 5 seconds inclusively? So to do that, we have the probability that this is our x, that's our random variable. Over here is our alpha, so alpha is equal to 2. And because it's standard, our beta is equal to 1. So what we're asked is the probability that 3 is less than x, which is less than 5. So we can also then rewrite that as x is less than 5 minus the probability that x is less than or equal to 3. And so what we need is we need to use our cumulative distribution function. So what we need is, and we're going to use our gamma, our standard gamma. CDF. So in this case, it would be 5, and our parameter for this would be just 2 minus, and in the second case, we'll have 3, and we still use our alpha of 2. And so then going to and I will be able to, so you can go back and pause it. The other thing you can do is I will be scanning these notes afterwards so I can send them out to you. So we can go back to our incomplete gamma function here, or this is our table A4. And so what I need to look up is 5. So x is 5 and alpha is 2. So I need this, which is 0.96 minus, and then I look for the other one I need to look up is 3. So that's 0.801. And subtracting that, I get 0.159. The next part we have here is, what is the probability that the reaction time will be greater than 4 seconds? So again, what it's asking is, what is it that's greater than 4, which means that I need to look at the complement because I want to use the CDF. So I need again, it's the standard gamma CDF, and that's where, so this one is where it's x, and up here, this is where it's alpha. I should just kind of put that in little. So same thing again here. 1 minus, and I need to look up x is 4 and alpha is 2, so that's 0.9, which we had already looked up. Oh no, we hadn't. 0.908. Subtracting that, we're left with 0.092. Yes, those tables will be provided during the test. We don't expect you to memorize this. We definitely don't expect you to numerically integrate it, so that's why we give you those tables. So the next part, here's another example. So suppose that the survival time X in weeks of a randomly selected male mouse exposed to 240 rads of gamma radiation. How appropriate, we're using a gamma distribution with alpha equals 8 and beta is equal to 15. So in this case, we're asked what is the expected survival rate of a male mouse exposed to 240 rads of gamma radiation. So I'd like to point out it's the radiation that is killing the mouse, not the probability distribution. So we have the expected value is equal to alpha times beta. So alpha is 8, and we multiply that by 15. And so, let me pull out. 8 times 15 gives me 120. The next one that we're asked is, what is the variance of the survival time of a male mouse exposed to 240 rads of gamma radiation? So for this, again, using our formula, which is alpha times beta squared, we have 8 times 15 squared. So 8 times 15 squared. So that's 8 times 225, and multiplying that together gives me 1800. What is the probability that this randomly selected male mouse will survive between 60 and 120 weeks? So this is something else I should probably write down. The expected value is 120, and it's what? And this is important that I should have noted it's in weeks. So we expect the mouse, a male mouse, if we randomly select it, to be surviving for 120 weeks. And same thing, that's the variance. So now we should convert what this says in words to symbolically, and that means that it's the probability of X, which is between 60 and 120. So again, I can use my distribution, my standard normal, or sorry, my standard gamma. Now with the standard gamma, I need to have one parameter. So the way that we had done that is that it's going to be alpha over beta. So in this case, alpha is 8 and beta is 15. So it's 8 over 15. Oh, nope, you made a mistake. I made a mistake, not we. I did. So there's a question in the... Why do we use standard gamma if b isn't 1? But b is not 1. Okay, so let me just go back. Oh, and there's I made a small error. Because what I wanted to do was from 0 to x over b. And instead what I had written was alpha over b, and that's not the correct way. So let's fix that. So what it should say is from alpha, it should be alpha, and what I'm doing is I need to rescale it from not x, but then x over beta. There we go. So the previous example that we had done is fine because, again, beta was equal to 1, so I didn't have to rescale the x. But in this one, I do. So what I need to do is 120 divided by the beta, and the beta in this case is 15, and the alpha still is 8. So does that answer the questions in the chat? 60 over 15 gives me 8. Okay, perfect. And I have 60 over 15, which is 4. So again, I look up my table here. I have 8 and 8. So I need, make sure that so 0.547. Minus, and over here I need 4 and not the 8, so it's 0.051. And subtracting that gives me 0.496. And lastly, we're asked, what is the probability that the mouse will survive at least 30 weeks? So with this, it's asking us what it is greater than 30. So again, taking the complement. So 30 divided by 15 is 2. So I have 2. And let me grab the table again. Again, I look at for 2 and 8, and it's 0.001, which means that the probability is 0.999. So that's a good question. If it says if it's at least, should it be, or does it? I am a little sloppy when it comes to continuous random variables. Yeah. When it comes, because it's at least 30 weeks, yes, I could write it like this, and this still holds as well. So I could write x is greater than or equal to 30 is equal to 1 minus. Yep. It does, in this case, it doesn't matter because it's continuous. Yeah. But I should be precise, and that's very good that you're pointing that out. So that's the gamma distribution. And so again, we can do, just as a little side note, I should probably show that when we're using that, it's f is x over beta and the parameter alpha. Okay. So the next thing I need to talk about is discrete jointly distributed random variables. That is a mouthful. And if you want to get to what we're going to basically do, I'll just skip down to this part right here. this is, instead of basically using one random variable where we have like a table where it only has one row or one column. So here is just one variable and this sums up to 1. While over here, now I have 2 random variables. And they form a table. That's it. That's all that we're going to be for 2 random variables. So let me just go back up to that formula. So it's, if we have x and y is 2 discrete random variables, then we can have some probability mass function, or the PMF, where it describes both. So it's the probability that it equals the value x and the value of y. The other thing is that each of those values that we have, the probability for those 2 random variables, has to be non-negative. And that if you sum over either the row or the column, that you should, that if you sum over the entire table, it should sum up to give you 1. So over here, what I can do is check that each of these values are greater than 0. And if I sum them up, so if I take out my calculator, I have 0.2, 0.1, 0.2. So over here, what I'm going to do, for reference here, I'll put this over here as 0.05. And if I add down this row down here, 0.05, 0.15, and 0.3, that gives you 0.5. So again, if I add that up then, so all those entries sum up to give me 1. The other thing, whoops, shouldn't have. If you do it this way, so you have 0.2, you get 0.25, 0.1, and 0.15. Get a quarter. And here, you get 0.5. So again, you have 2 quarters and 2 quarters here, so you have 1 as well. So it sums up to 1 in one direction, it will sum up to 1 in the other direction. And over here, this is what we'll call a joint probability table. And so what was I doing over here? Well, traditionally, when we have lined paper, something like this, when we have a line or if we have something like this, this is called the margin, okay? We have that margin on the side here. And so what I was doing was I was summing up the probabilities in the margin. I drew a margin in here and I calculated it. And so that is what we also have with 2 random variables. We have what's called the marginal probability mass function, or of x, and we also have it for y. And essentially all that is I'm summing up along a row or a column. So in this case, if I wanted the probability mass function of x, it's for a particular value of x. So if x is equal to 100, then for that row, if I sum them up, so 0.2 plus 0.1 plus, that gave me 0.05. And if I have, for the second row, the 250, I add that up and I got 0.5. Okay. And if it's any other value of x, so otherwise, it's 0. Okay, and similarly, we can do the same thing for y. So instead of going along this, instead of going down the rows, now we'll be going down the columns. So if y is equal to 0, if y is equal to 100, and if y is equal to 200, and the last case we have otherwise. Oops, I should extend my bracket. So if y is 0, then that's 20.25. If y is 100, then it's 0.25. And lastly, if it's y is 200, it's 0.5, and 0 otherwise. So those are the marginal probability mass functions of x and y. What we can do then also is we can calculate the expected value of this. So to calculate that, now I need to use my marginal function. So this is the expected value of x, and this is the expected value of y. So over here, I need to calculate using this marginal function. So this is the marginal PMF of x. And that's multiplied by the value of x. So I need to do 100 times 0.5 plus 250 times 0.5. So that's 100 times 0.5. That gives me the 50 plus the 250, and multiplied by a half is 125. Adding them together gives you 175. And similarly over here, this is for our example. This is kind of our running example here up here. For the y, I need so 0 times 0.25 plus 100 times 0.25 plus 200 times 0.5 and 0 otherwise. So I don't have to worry about the other case. I don't have to worry about that because that goes to 0. And so I have 100 times 0.25, that gives me 25. And I have 200, and I need a half of that, which is 100. So that gives me 125. And instead of just a variance, when we have two random variables, we have what's called the covariance. Now, this is one way that you can do it. You can use this formula. And there's another formula that we can use as well, which is the other formula, and which is equal to the expected value of x minus mu x times y minus mu y, and so that's our formula for that. So I should just put this in some boxes. So we have a box here. We have a box over here. This is important. This is one formula for it. Here's another. So for our example, I should try to keep the expected values up there. So for our example, so here's our definition. So what this says is that we can have the summation over, we could do either x or y, so let's do x and y. And in this case, it'll be x minus, and our mu of x was 175. And for our y, it was y minus 125. And we need to multiply it by the probability of it happening, which is p of x, y. So I don't need these values at the moment because I've already put them in my formula. But what I do need is, oh, good thing I got a wide screen so I can show everything. There we go. And move this out of the way. So there is our joint probability table. So over here, this is equal to, I have to have, and I'm going to slowly work my way through each of these values. So here I would have 100 for x, so that's 100 minus 175, and that is for 0 for the y, so 0 minus 125 times its probability, which is 0.2. Then the next part is I have 100, so there I'm still with 100, minus 175 times 100 minus 125 times 0.01. And the next one I have is 100 minus 175, 200 minus 125 times the 0.2. So that's done for the first row. I have to still do the second row. So I have 250 minus 0. So I have 250. Oh, I have to be careful. Whoops. No. So it's 250 minus the expected value of x times 0 minus 125 times 0.05. So as you can see, I'm just slowly working my way through the table. And the last one, $200 minus 125 times 0.3. Okay, so somebody is saying, I'm not clear about this. Which part aren't you clear about it? How we are selecting the numbers. Okay. So just to go through that once more. So I have my x value and I have my y value. So that it will be my x minus 175. So there is my, so right through here, this is my mean. So if you notice here, on each of these, there's the mean. Okay. And over here, there's my mean of y. So there is my 125. Okay. And then each of these values here, I need to go through. So in this case, let me use a pencil so I can erase stuff. Do I have one? There's a pencil. So for instance, I'm looking at, here's the value. This is my value of x. This is my value of the probability of x and y. And here is the probability of y. Sorry, the y value. So in this first case, in this first line right through here, what I have is there's my x value of, there's 100 minus, again, the mean. Then the next one is I have the value of y, which is 0, minus the expected value of y, times the probability right there. So if I do it like that, here's my value, there's the y. Let me grab another color. Here's a green. And lastly, here's the value of the probability. Okay. So what you do then is I'm just working through the first row. So I have, for that next one, I have 100, which is still the same here. And I want to do this one. So I'm looking at this value here. So that's the probability right there. And 100 is my x, and my y is 100 as well. Okay? So if you calculate that, so that's, you just put it into your calculator. You should get 1,875. So I would say just as a recommendation, I would say use this recommend this for calculating two discrete random variables. Okay. So this is the end of the material that we've covered then for the midterm. So yes, you will have to know how to do a discrete jointly distributed random variable, how to calculate the marginal probability mass functions of x and y, and you will have to know how to calculate, say, the expected value of x and the expected value of y, and you should be able to, as well, be able to calculate the covariance. So yes. So x and y, I should make sure that people don't get confused. The expected values and the covariance. Okay, is there any questions before we finish for today? Just to be sure, how far back does the material cover for the midterms? So that was what we covered at the beginning of the lecture. And, oh, just a second, let me grab what I had written. It will cover 3.4, 3.5, 3.6, 4.1, 4.2, 4.3, 4.4, 5.1, and 5.2 for the discrete case. So 3.4, that goes back to the binomial distribution. Okay. Thank you everyone for tuning in, and I will see you all in person on Thursday. If you have any further questions about the midterm or questions about practice problems, feel free to send me an email. The other thing I will say is if you are going to do practice problems for 5.1 and 5.2, I would just make a little note here. So for the practice problems. Focus on discrete joint RVs. Okay? Okay. Take care, everyone, and have a great day.